Hi, I'm Filip Aronshtein.
And I am Peter Weiss.
And this is our low pass and our band pass filter. So we're going to do the low pass first. So what we have here is two resistors in parallel
That together have a parallel equivalent resistance of about 1.5 kilo ohms, a little less than that.
Yeah.
That's the best you could do.
So they are in series, and then they come to a point where they connect with a capacitor of 0.001 microfarads, and that gives us a low-pass filter that gives us a frequency response that looks like this.
So the top diagram is the gain, and you can see the gain, the yellow is the input and the blue is the output. So the gain of the output is around 0 for all the low frequencies, which means it's the same as the input, so it passes those frequencies. But then once it gets to a certain value, the gain gets really small, so it basically does not pass the frequencies above where the gain is around -3 decibels, which is a little more than 100 kilohertz in this example, just because of the values that we use. And then we also have this frequency response here, so when the gain is 0, when it passes the frequencies, the phase shift is around 0, but then once it stops passing the frequencies, the phase shift increases or decreases, and it gets to be about 90 degrees out of phase, because the capacitor takes time to transfer the charge and do its work. So that's why we get an out of phase when the gain is lower.
Yep. So next we've got our bandpass filter. So what this looks like is the following. Let me just clip this in, scope it. Okay, great. So we have a resistor that connects to a inductor and a capacitor that are in parallel, which then lead to a point in the ground. We are scoping across the inductor and again across the input. And the frequency response looks like this. So we see that it peaks at a resonance frequency of just under 100 kilohertz. And
so that's where the gain is 0, and that's where the source is about the same as the output. So the output, these frequencies get passed, but then once the gain drops below around -3 decibels, like right around this resonant frequency of a little less than 100 kilohertz, that means it does not pass these frequencies. So these frequencies do not get passed, but the frequencies here in this narrow range do get passed. And the phase response, we have a phase shift of around 90 degrees here and around -90 degrees here, so that's the frequencies that don't get passed. And for the frequencies that do get passed in this range, it's around a phase shift of 0. I mean, it's not a quite steep a slope as we would like to see, but for the frequencies that get passed, it's around a phase shift of 0, and it's 90 degrees out of phase in one way or the other for frequencies that don't get passed.